Hi. Okay. Starting off this week with Module 13, Section 5.4, and this finishes up Chapter 5 for us, Bifurcations for Systems. So the whole goal of this section is just building on what we've seen before and just showing you how the fact that we've classified linear systems using the trace determinant plane makes it possible to all do kind of fancy phase plane analysis of nonlinear autonomous systems. So we're looking at systems of this form where we've got two dependent variables, x and y, and we've got alpha, some parameter, and we're looking at bifurcations for alpha using that trace determinant plane. Okay, so we'll start off with a system we know quite well, the spring mass model. The equation is mx double prime plus bx prime plus kx equals 0. So in the book, if you look at section 5.4.1, it looks at x double prime plus bx prime plus 4x equals 0. And as that parameter varies, you get a horizontal line in the trace determinant plane. The horizontal line determined equals 4. And you look at where that horizontal line crosses the special cases, and that's at -4, 0, and 4, right? It's at where it crosses the parabola and the vertical axis. And so it goes from a source to a spiral source to a spiral sink to a sink. Of course, the only one that's physically relevant is the one where b equals 4. And so that's where it goes from a spiral sink to a sink. So just to give you another example, let's look at x double prime plus 3x prime plus kx equals 0. So we turn that into a system in the standard way. X prime equals y, where y is the second derivative, so y prime equals minus kx minus 3y. So we put that in matrix form. We know the only equilibrium is the origin, it's a linear system. The Jacobian is the matrix itself, right? Because if you linearize something which is linear, you get the line back. So we see the trace is -3 and the determinant is k. So as k varies, we get now a vertical line in the trace determinant plane. So that's the line trace equals -3. We see, again, where does it cross the special case curves? The horizontal axis, well, that's when k equals 0. So this is a bifurcation. It's not physically relevant to the spring mass model, but it's where it goes from a saddle to a sink. And there's another bifurcation where it crosses the parabola, and so it goes from a sink to a spiral sink. And the module question for today is, what value of k is that? Okay, so let's have a look at some biology examples. So again, if you go to the text, you look at that there, section 5.4.2, it looks at a predator-prey model where the parameter that we're studying is the carrying capacity of the prey. So we can see that there are 3 equilibria where both species are extinct, where there's no predator, so that the system is at the carrying capacity of the prey, and there is a coexistence equilibrium, 2 minus 2 on n, 1. So if you look at section 5.4.2, it'll give you analysis of this. Your second module question is not looking at the Jacobian at all. Just by looking at the formulas for the equilibrium, you can tell that there's a bifurcation at n equals 1. Why is that? So instead of looking at that model in detail, looking at another one. This is a cooperating species model. Here we've got two species. There's a logistic equation for both of them, but now somehow they cooperate. And so that's what, there's a plus some positive term times x times y. So this happens, you know, like bees and flowers, or ants and the ant tree, right? There's a tree where ants can live in, make their nest in that. And so in return, the ants protect the tree from herbivores, which they'll go out and attack anything that tries to eat the plant. Okay. So this time there's 4 equilibria, both species extinct. There's 2 cases where there's only 1 species present, and so then we would expect that species to be at carrying capacity. And there is the coexistence equilibrium, where the 2 non-zero null clines intersect, right? So the 2 non-zero null clines are 2 straight lines. They'll intersect at 1 point. So you have to do a bit of fancy linear algebra. Well, not that fancy, it's just linear algebra. So we can solve it as a matrix, right? Because if you take those 2 straight lines, you can turn them into a system. Basically, you can turn it into 0.2 divided by n times x minus 0.1 times y equals 0.2, and minus 0.05 times x plus 0.2 times y equals 0.6. Write that as a matrix, and you invert that matrix and multiply that by the column vector 0.2, 0.6, and you get your answer there. And you see that in the coexistence equilibrium, the populations are much greater than if the species was just by itself. The whole idea of cooperation is, you know, they can have a higher carrying capacity because they help each other in some kind of way. Okay, so to analyze this, we look at the Jacobian, and at 0, 0, we plug in 0, 0, we see that we get the diagonal matrix 0.2, 0.6. They're the eigenvalues, right? Because a diagonal matrix, the eigenvalues are on the diagonal, got positive eigenvalues, so it's a source. At the 1 species equilibrium, we get triangular matrices, and again, the eigenvalues are going to be on the diagonal, and in both cases, we get a positive eigenvalue and a negative eigenvalue. Right, so in one direction where we're just looking at where just the species is just by itself, it's going to be stable. But the fact when you add the other species, just have to add just a single individual from the other species, it's going to help that the other species to thrive. So that's going to be unstable in that direction. Okay, what happens when there's both species around? Okay, we plug x star y star into the Jacobian, and at first we think there's a mess, but there's a nice little trick to use, which is the fact that the definition of x star and y star is that it's where those 2 non-zero null clines meet. So it's going to be, so we know by definition 0.2 times 1 minus x star on n plus 0.1 y star equals 0.6 times 1 minus y star on 3 plus 0.05 x star equals 0. Okay, so we can make part of the Jacobian equal that stuff, which we know is going to be 0, and so we get a simpler Jacobian matrix. Simple enough so that you can figure out what the trace and determinant are. So for a start, the trace is always going to be negative because both terms in the diagonal are negative. And then when you look at the determinant, do AD minus BC. You see you've got an X star times Y star in both terms there, so you can pull that out as a common factor, and we get 0.04 divided by n minus 0.005. And that's positive when n is less than 8. Great. So we know for stability, we want a negative trace and a positive determinant. So the coexistence equilibrium is stable for n less than 8. And there's a bifurcation at n equals 8, which we could have seen earlier, because when we look at what the equilibrium is, we see in the denominator 40 minus 5n. So when n gets to be 8, we're dividing by 0. So when n is greater than or equal to 8, both populations are going to just zoom off to infinity. Okay, so let's have a look at this with maxima. Okay, so this is a situation where n equals 3, and if we just click somewhere here, we see the arrow going towards our stable equilibrium right there. Oh, from all directions it goes there. Great. And so n equals 3, but we can see that the carrying capacity for x was 3, and for y is 3, but we can see that the equilibrium for, is much more. It's like 12 for x and 6 for y. So they can support much greater populations because of their cooperation. Okay, and then here is when n equals 12, and it's just going off to infinity. Okay. Okay. What's our next example? The example in 5.4.3 has like 6 parameters, and it's really complicated, so you can look at that. But for a system where we look with more than one parameter, I chose this. Here we've got 2 parameters. So we've got a predator-prey system, and for the prey that which is modeled by X, it's not the simple logistic equation. I've incorporated what's known as the alley effect. That's a situation where if a population gets too small, then it can't possibly thrive. The idea that it needs a certain number to be able to have a sustainable population. And so we're going to let A be greater than 2, and it measures that effect that of the population dying out if X gets too small. And epsilon is just the effect of the predator on the prey. So it's a negative interaction between the predator and the prey. Okay, so the X null clines are then X equals 0, and that quadratic equation then. And the Y null clines are Y equals 0 and X equals 1/2. So if we let Y equals 0, i.e. that means there's no predator, there are 3 equilibrium, 0, 0, where both populations are extinct, and then 1 on A, 0, and 1, 0. So there's 2 stable populations for just the prey. One where it's at carrying capacity, and one when it's at 1 over A, which is just basically just a small population, and the alley effect is bringing it down. It's sort of counteracting the natural tendency to exponentially grow. Okay, and when X equals 1/2, we plug in X equals to 1/2 into that X null cline, and we get Y equals A minus 2 on 4 epsilon. Okay, so we we can figure out what the Jacobian is again. Again, at 0, 0, we plug in, we get a diagonal matrix, but this time the eigenvalues are negative. Okay, and so that tells us that the origin is actually a sink. At 1 over a0 and 1, 0, again, we plug in those values for x and for y, and for example, at 1 over a0, we get that the eigenvalues are 1 minus 1 on a and 1 on a minus a half, and that's going to be a saddle when a is greater than 2. Okay, because 1 minus 1 on a is always going to be positive, but then 1 on a minus a half is going to be negative when a is greater than 2. And then at the carrying capacity equilibrium, we get as our eigenvalues 1 minus a and a half. And so when a is greater than 1, we have that to be a saddle because we've got a negative and a positive eigenvalue. Okay. What about the coexistence equilibrium? We plug that in and we do some algebra. So lots of things cancel, and unbelievably, the first term just gets to be a half. Okay, so we see that the trace is a half, and the determinant is a minus 2 on 8. So since a is greater than 2, that's positive, but the trace is determinate also. Okay, so this means it's an unstable equilibrium. The discriminant is the trace squared minus 4 times the determinant, and do a bit of algebra, and we see that's 5 minus 2a divided by 4. And so we see we have a bifurcation at a equals 2.5, and that's where it goes from a source to a spiral source. And we see that epsilon does not have a bifurcation. It affects what the equilibrium populations are, but when epsilon changes, it actually doesn't change the nature of the equilibrium. And so we see that the only stable equilibrium is the origin, and so the long-term behavior is extinction for both species. No matter what value of epsilon we get, it's going to be extinction for both species. Of course, because once the prey goes extinct, the predator goes extinct as well. Okay, that's today's module. Next time we look at chapter 6 and Laplace transforms.